Sorry, I forgot to turn on the screen. All right, so carboxylic acids and derivatives. So we're moving into a next section. We finished up aldehydes and ketones. If you did not have a chance to look at the lecture, it was all about synthetic strategies. That's going to be something we're going to continue to harp on the rest of the semester. So we'll look at new reactions and then we'll embed those in our synthetic strategies. Okay, and we'll look at some problems on that at the end of the class today. But moving forward, carboxylic acid derivatives. Carboxylic acid is a carbonyl with at least an OH attached, right? So this is our basic structure. And the reason that we're looking at carboxylic acid derivatives in the same point is that we have a group of molecules that all have related chemistry. So like with aldehydes and ketones, a lot of the chemistry was identical. Every once in a while, there was a little variation between the two, but they're very similar. Here, it turns out that all of the derivatives can be converted to carboxylic acids, and all the carboxylic acids can be converted to all of the derivatives, right? And most of the time, when you're going from the carboxylic acid derivatives, it's a simple hydrolysis. The conditions may be slightly different, but it's just a hydrolysis. And going from the acid to the derivatives, again, it's usually a straightforward process. So these are kind of interchangeable. So if we look at that, the first one is our carboxylic acid, right? So this is our group of acids. You're going to know them because they're going to have a carbonyl and OH. If we look at our esters, the difference in our esters is we'll have a carbonyl and then an OR. Acid chlorides, again, we've got a carbonyl, but now the carbonyl is attached to a chloride or potentially a bromide, although those are rarer. In shorthand, this is known as an acid chloride, or would be known as an acid bromide, right? Long term, it is carboxylic acid chloride, right? But often we short that down to acids, and you'll even see sometimes the book will just call it a chloride. If we take a carbonyl with an oxygen and another carbonyl, right? This one is known as an acid chloride, acid anhydride. And the anhydride here, oh, my spelling is horrible. My anhydride, right? Anhydride means without water. So if we think about the anhydride, you could think about two carboxylic acids coming together, right, to make an anhydride plus the water, right? So if you remove water, that's how you get an anhydride. It's similar to that easy in the retrosynthesis, but this is the concept. We also have amides. And you can have a primary amide or you can have a secondary amide. Then the last one that seems not to fit because it doesn't have a carbonyl is the nitrile. But the reason it fits is that I can hydrolyze, and we'll look at that reaction today. I can hydrolyze the nitrile to the acid. And we also saw that when we looked at a hydrogen cyanide addition to carbonyls, right? That was one of the next steps. You could hydrolyze that off to get the alpha hydroxy acid. So we're going to be looking at these sets of reactions. Now, these sets of reactions, this chapter usually gives students a hard time for a couple of reasons. One, if you've been trying to blunt force memorize all the reactions, this one's going to be difficult because there's very subtle differences in these reactions, right? So when we look at hydrolysis to form carboxylic acids of these, some only use water, some use water and acid, and some use water, acid, and heat. If you understand the reason which has to do with the leaving group, which we'll talk about. Then you'll understand why you need to go from simple water to water and acid, and then water, acid, and heat. Understanding the mechanism and the base reason for the differences is going to be the way you keep this straight, right? If you've been just kind of blunt force trying to memorize all of these reactions, this is usually the chapter that throws those students off. If you work through the mechanisms and you think about the reasoning for the differences, then this chapter really is a few reactions with slight derivatives, right? It's almost all the same reaction, just slight differences. So I've got a Camry and an Ultima and a Cord, and they're all about the same, right? But if you try to blunt force it, you're going to have a hard time. Okay, so when we're going through these, please focus on the reasons, especially when we get into the differences in the derivatives. Okay, for carboxylic acids, okay, there are some names that are very common, and therefore they are IUPAC accepted. Acetic acid is the main name for this. It can also be known as ethanoic acid, but you won't see that written anywhere. Right? You'll always see it as acetic acid. If you notice, it's 2 carbons, and then we're using the oic acid. So if we add more carbons, right? So here we have 6 carbons. This is going to be hex and oic acid, right? So we're using the oic acid as my suffix. Since it can only be an acid if it's on the 1 carbon, you don't have to say that, right? The oic acid is a high priority group. It's got 3 bonds to oxygen, and it's going to most often take priority, and it's always going to be 1, right? Everything else is going to be different because the acid is there. And if you ever wanted to know the chemical that makes dirty socks smell, well, dirty, it's hexanoic acid. If you want to know what makes goats smell like goats, it's pentanoic acid. And then we have biologically, acids are pretty important, right? Here is lactic acid. Because they're biologically important, you have a lot of common names, like lactic acid is a common name. This could be also 2-hydroxy propanoic acid. Right, but you'll only see 2-hydroxy propanoic acid on the chemical bottle in a chemical lab. Right, everybody knows this. Lactic acid is what makes your muscles hurt, but it's also what makes milk taste sour when it goes bad. Okay. So naming convention for these is pretty straightforward. When we look at acetic acid is one of the most important chemicals industrially, but there's 2 distinct differences on how to make it. So it is important when you go to buy vinegar, you may want to read your label. If you take ethanol and have it with ozone in an enzyme, right, you can make acetic acid, right? And this is traditional vinegar. So you take old wine and you add the proper enzyme, and the proper enzyme is usually in a bacteria, and just leave it exposed to a little bit of oxygen. What's going to happen over time is that ethanol is going to be oxidized up to the traditional vinegar, right? So you might see balsamic vinegar. You need to read the label. It should have come from wine, right? So balsamic vinegar. What you would like to see is consumable vinegars, right, are made from ethanol. Industrially, though, there is a process where you can take methanol and carbon monoxide with a rhodium catalyst, and that will also make acetic acid. Now, this one also can create food grade acetic acid. And so sometimes you will not see any reference to wine as being part of the process. If that's the case, especially in very cheap white vinegars, most likely it came from this process. And of course, if you buy a 55-gallon drum of acetic acid, it's going to come from this process, right? Where we take methanol, react it with carbon monoxide with rhodium. Let's name this one. Bless you. Okay, let's try and name these two. So if we look at the first one, we get 1, 2, 3, 4, 5 carbons. So this is going to be a pentanoic acid. And then on our third carbon, we have a methyl. On the next one, we have 3. So this is going to be propanoic. Right. And then we have the 2-chloro. Questions about either of those? We can also have a species where we have a carboxylic acid on the side, like this one. Okay, this is not a benzene, right? The benzene would be benzoic acid. In this case, we're going to name it as a cyclohexane. Right, so that is the 6-membered ring. And then to name the 1 carbon on the side, we need a carbon for that. So we're going to add the name carbo. Right, so carboxylic acid. So if we look at our number of carbons, the 6-membered ring is a cyclohexane, and then that carbo, and you'll see this carbamide, you'll see carboxylic acid, carbon, carbo anhydride, right? So anytime you see that carbo, it's that 1 carbon plus that side group. We can also have diacids. So here we have heptane dioic acid. So we're using the dioic, right? But also notice that we add the E back in so that we don't have the N and the D together. In diacids, we have a few very common names. So this one is known as oxalic acid. And this one is malonic acid. And you'll see both of those names again used quite readily in the text. So the main reaction with carboxylic acids is the fact that they are acids, right? So this dissociation of the proton, right, is going to be the important reaction. So carboxylic acids acting as acids is the main reaction we're going to have. And because that transfer of that proton is going to be faster than other types of reactions. If it can act as an acid first, it's going to act as an acid first. The pKa here is 4.76 for acetic acid. Give you an idea where that sits, right? If we had ethanol, that's going to have a 15. That's going to have a 16 pKa, right? Water is 15.7. But if we get to something like hydrochloric, right, we get -7. Right? So we also have the possibility of modifications. And so this is going to be important in determining reactivities. So if we have an electron withdrawing group, what's happening here is, right, you got the negative, and then inductively, what's happening is we're getting a pull of electron density away from that ring, right? So therefore we can see 2.7 is more acidic than the other positions. Also, we're going to start using the different locations. So if it's 1 away from the carbonyl, that's an alpha position. 2 away is going to be the beta position, and then 3 away is known as the gamma position. So you can see here that that alpha has a pretty big effect, right? But then when we get to the beta, the effect is decreased. It's because I'm going through more sigma bonds. This is an inductive effect, not a resonance effect. And then when we get to gamma, we see an even greater decrease. So usually these impacts drop off when we get to about 5 or 6 sigma bonds. Okay. Questions about acidity? So if we look at preparation of carboxylic acids, we already know some of these, right? So if we take an alkyne, react that with ozone, followed by water, we're going to end up with a carboxylic acid. Okay, and this is a review reaction. We've already seen that one last semester. Of course, if it's symmetric, you end with 2 of them. If it's not symmetric, you'll end up with 2 different carboxylic acids. We can also do oxidation of primary alcohols. So if we use our sodium dichromate or potassium permanganate or chromic acid, we can end up with a carboxylic acid, right? So primary. And then as long as we have a beta hydrogen, right, we can do a benzylic oxidation. And again, either sodium dichromate or chromic acid. Can oxidize that. So we've seen these before, right? The first two we saw last semester, and then this last one, we covered that a few weeks ago. Okay, questions about these reactions? Notice with the ozone, we're not using the DMS or zinc or hydrogen peroxide, it's just water, right? So that's one of the distinct differences there. So for our new reactions, we have hydrolysis of nitrile. And this was introduced in the last chapter. Okay, and then this is one of the ones where we need acid, water, and heat. And we'll look at one of the reasons for that in a later section in this chapter. So if we look at the mechanism on this one, we protonate our nitrile in the first step. That activates this nitrile to attack by the water. We get a proton transfer. And then we get another proton transfer. And then we have lone pair come down from the oxygen. Pi bond goes back to the nitrogen. And really, I should be showing you that these are all reversible steps. If I had removed water, I could do it the other way. Okay, and I'm going to rotate this if you don't mind. Again, proton transfer. Okay, and if we notice, what functional group is this? That's an amide. Okay. So if we add a proton, another proton transfer, this time to the nitrogen. And then we can get and again, this is reversible. It's driven forward by and then last step, proton transfer to get us to the product. To the carboxylic acid. Whew, lots of proton transfers. So hydrolysis of nitrile. Water, acid, and heat. So we proton transfer, water attacks the activated nitrile. Then we get proton transfer of nitrogen. Now the oxygen displaces the nitrogen as the double species. Proton transfer. Now we get an addition of water. The thing, second step, it could go backwards or forward, right? Kick off the ammonium, and then we just get proton transfer to get us the carboxylic acid. Okay. All right, questions about this one, other than you hope you don't have to draw this whole mechanism from memory on every single exam from here on out. I'll take that under consideration. So, okay. That's the first new one. The next one is carboxylation of Grignards. And this one has a much more straightforward reaction mechanism. If we take a Grignard and react that with carbon dioxide, followed by an acidic workup, we can end up with the carboxylic acid. If we look at the structure of our carbon dioxide, it makes sense why this reaction occurs the way it does, right? Carbon dioxide is a carbon with a double bond oxygen. Well, that looks a whole lot like a carbonyl. It's not a carbonyl, but it looks like a carbonyl, and that's how it behaves. The Grignard attacks the carbon in the middle, right? The electrophilic carbon. Giving me this, right? So that's the end of step one. And then in step two, we add the acid. To get the carboxylic acid. If I wanted to go from this molecule to benzoic acid, right? Let's take a little time, see if you can come up with a good synthesis for this molecule, starting with benzene. Let's go ahead and take a look at this one. All right, so if we're going to add the carbon, right, and the fact that I asked you to do this right under there, signifying that maybe I want you to use that reaction, right? So we're going to add that. We can't use a nitrile because a nitrile can't do a SN2 substitution on a benzene ring. So what we need to do here is we need to create the Grignard. So if we think about it, I need to get to this, right? And as I did in the video, when you're thinking about these syntheses, don't worry about your reagents. Think about what can happen. So I can turn a Grignard into a carboxylic acid. So Grignard, what do I need to make a Grignard? Well, I would need to have a bromide, right? So I need a bromide here. And can I make a bromide from a aromatic? Yes, right? So the pathway here is going to be to go from the benzene to the bromobenzene to the Grignard to the carboxylic acid. Once you've laid out a step, and again, if you look at video, what you should think about is think about every transformation you can do for each functional group and start learning what is possible. It's kind of like you can get from here to Dallas without a GPS, right? It's pretty straightforward. But then if you think about it, how do I get from here to San Antonio, or here to Abilene, or here to Kansas City, right? If I know every point and where I potentially can get to from that point, really it's just I'm going to go to Dallas, and then I know Dallas can get me to Abilene. I can go to Dallas, and Dallas can get me to San Antonio. I can go up to Joplin, and then Joplin can get me to Kansas City, right? So what I'm doing is looking at the next step and then looking at all the possible places. So if you look at Joplin, right, I can go straight up and go to Kansas City. I could go over to Columbus, right? I could go over and down a little bit, and I can end up in Branson, right? So that's literally what you're doing with these understanding. Once I've made this transformation, what's the next transformation I can make, right? And trying to figure out a pathway from one to another. And the best way to strategy to do that is don't worry about your functional groups, worry about your pathway. So now we have the pathway. Now go in and put your functional groups, right? So if we're going to add, your transformation. So if we're going to go from the benzene to the bromobenzene, I need Br2 and FeBr3, right? I need a Lewis acid and the bromine. To create the Grignard from the bromide, I need magnesium and, diethyl ether, right? And the diethyl ether is telling me there's no water around. It's also the diethyl ether will stabilize the magnesium intermediate. And I drew this arrow the wrong way, so let me correct that. And then this last one, we just did this one, right? And so this one is going to be CO2, step 1, and then step 2, an acidic workup. Okay, so we have several preparations of carboxylic acids we've just covered, right? You've got some that are review. So we go back up all the way here. We've got hydrolysis of an alkyne. We've got oxidation of primary alcohols, and we've got oxidation of benzylic positions. Those three should be review. We've covered those before. Then we got a hydrolysis of a nitrile, right? And then we have carboxylation of Grignard. It turns out we're going to be adding some more, but as I kind of foreshadowed before, they're all going to be hydrolysis of one of the carboxylic acid derivatives. So we've got some more that we'll learn on, but right now we've got 5 reactions to make carboxylic acids. Okay, so let's look at reactions of carboxylic acids. Okay, and this first one is kind of a review because you have seen this before, which is taking carboxylic acid with lithium aluminum hydride. But you probably didn't spend a whole lot of time on it when you saw it in that reaction. So lithium aluminum hydride, we need to make a note here. Sodium borohydride won't work. Okay, so in aldehydes and ketones, I can either use sodium borohydride or lithium aluminum hydride. Here I have to use lithium aluminum hydride. Okay, now the mechanism here is a little different. The first thing that happened is not the hydride attacking the carbonyl, but if we think about a hydride, what's a hydride? Hydride's a negative, right? What's an acid? Acid is a positive. What's the first reaction that's going to happen if I put carboxylic acid in lithium aluminum hydride? I'm going to get an acid-base reaction, right? So the first thing that's going to happen is I'm going to create hydrogen gas and this. Then this reacts with the aluminum. I'm going to put R3 here because it turns out it could be many different species of aluminum. Let's turn that corner. Now that I have this, now another equivalent of the hydride can come in and do the reaction I was anticipating, which is the attack at the hydride. That gives me this species. I got the hydrogen attached here, OAlR3. Then these electrons come down, kick off this. This creates an aldehyde, but we know that lithium aluminum hydride will reduce we forgot the negative up there, will reduce an aldehyde. So hydride attacks that carbonyl. And then in the second step, right, we protonate. So a little bit of difference here, right? Instead of the hydride just attacking the carbonyl right off the bat, we get an acid-base reaction. Then we form the aluminum complex. Then we can go through and get the hydride attack to get to the final product. Questions about this synthesis? I mean, about this mechanism? You can also, although you can't use sodium borohydride, you can use boron in THF. All right, so this is just our oxymercuration demercuration reagent, right? BH3 and THF. This will also create the primary alcohol, but this one is more selective. So if I have a group that has a ketone and a carboxylic acid, BH3 and THF will reduce the acid in the presence of the ketone. And that means we have some different strategies, right? If I had done this with lithium aluminum hydride, I already would have had to have an excess because I need an excess for the acid. this case, I would have reduced both of those. Here, I'll need to add an excess because part of that reagent will be eaten up by the acid. And I will have to add a little bit of acid in the workup. So you can see here, if I use a BH3, it's selected for the acid over the ketone. The second one, lithium hydride, will work with both. So I reduce both of those. The ketone goes to the secondary, the alcohol, the acid goes to a primary. Acid reduction always goes to the primary because it's going to be terminal, right? And then if I use sodium borohydride, which doesn't react with carboxylic acids in a reductive way, it does in an acid-base way, but not a reductive way, then I can end up with reducing the ketone in the presence of the acid. As you might have noticed, carbon-carbon bond forming reactions are important. The other types of reactions that you should make special note of, because faculty like to ask lots of questions about them, is whenever you have these types of selectivities, right? I have 3 different reagents that will be selective to different functional groups in the presence of each other, right? The other way I can do this would have been protecting groups, but if I have a selective reagent, I can use a selective reagent. I don't have to worry doing the protective. Okay. Questions about these? There will be a few other reactions of carboxylic acids, but the way the book does this is it introduces those carboxylic acid reactions as preparations for the acid derivatives. Now, as we kind of talked about before, if we look at a carboxylic acid, we can use the carboxylic acid. Right. This transformation is possible. We can go from the carboxylic acid to the anhydride, to the acid, to the anhydride, to the chloride, to the amide, to the nitrile. Oops, wrong structure. We can also take all of these and I'm not putting the conditions here. We'll go over that as we get to each one of these. And hydrolysis of each of these derivatives will result in the carboxylic acid. Okay, so the nomenclature on these, when we look at acid chlorides, we're going to change the suffix to acetyl or ill chloride. Right, so this would have been butanoic acid. We replaced the oic acid with the IYL chloride. So you can kind of think about these names as modifications of the acid. Here, if we have this one, this would be acetic anhydride. Here, we're keeping the acetic part, we're adding the anhydride. If we have symmetric, anhydrides, and we only really need one name. So if you see a butanoic anhydride, that means both sides are going to be 4 carbon groups. You see acetic anhydride, that means both carbons are going to be 2 carbon groups, right? But if we have unsymmetric, we're going to need to use both names, right? So in this case, the propanoic and butanoic would be the acids. So therefore, we're going to use that, and this one's going to be butanoic, propanoic anhydride. Yes. Yeah. Yeah. Oh, that one. Yeah. Okay. So if it's symmetric, you just need one name. If it's not symmetric, you need two names. For esters, here we're going to use the ate suffix. So this becomes acetate, right? So we're going to add the acetate, and then in front is then the substitution. Where this name comes from is that if I had this, right, that would be an acetate. So the ate usually refers to a negative species, right? So we have ates and ites. So you have sulfate, sulfite, nitrates, nitrites, right? It's usually in a negative ion. So what they did here is they said, okay, what if we pretended that was a negative ion, and then we added the ethyl to it as if we were doing a metal. And so the name kind of derives from that. So if we had sulfonate, we'd have sodium sulfonate, the metal sodium, and then the sulfonate. Here, the ethyl acetate, right? So that's where the logic of the naming system came from. So in this other one, then we're going to have count the number of carbons, right? 1, 2, 3, 4, 5. So this is going to be pentanate, right? So pentanate. Pentanoate. Sorry, 08. I knew that sounded funny. 08, right? Because it'd be pentanoic acid. So we drop the IC and put the ATE. And then this one has the methyl attached. And notice the methyl is not the same. It's 2 words. So there's a methyl space pentanoate. There's an ethyl space acetate. Questions about this one? And the reason for the space versus no space, this is confusing, is because they're using a nomenclature system based on the assumption of a metal, right? And if I had sodium sulfate, there would be a space, 2 words, not 1 word. For amides, we're going to use the acid amide. So we're just going to name it as an amide. But with amides, we have the possibility of different groups attached to the nitrogen. And like with our amines, we're going to use NN to say where the methyl groups are. It's not enough to just put dimethyl because I potentially could have methyls attached to the carbon side, right? So I need to put NN there for a dimethyl. I put an N for a monomethyl. Okay, questions about these? Like with our carboxylic acid groups, if we have something on the side, right, we're going to want to sorry, I'm putting the ester name, carboxamide, right? So again, we're using the carbox, right? Tells us we have the carbon, and then the amide tells us the function group. For nitriles, we're going to name them as nitriles. So this is going to be acetonitrile. One of the differences is I can name this as a cyano side group. So we could name this as 1-cyano or just cyanocyclohexane. So sometimes nitriles will be named as cyanos, as side groups, where you don't usually see that with your other carboxylic acid derivatives. Question about these? Yes. I can't hear you. The first one up here. So the cyclohexane, we've got the 6 carbons, but like with the acid, we name the 6 carbons and then we put the carboxylic acid on the side. Here we just put carboxamide. Right. So if we go back up to here, we're naming it all the way back. Where did we do that? This one, right? So we named the 6-meter ring and then the carboxamide, but the carboxylic acid side group, right, is the parent. The difference in the cyano is that we're naming it as the non-parent. And the carbo is what's giving us that 1 extra carbon, right? So it's cyclohexane, carbo is that carbon, and then the functional group. So carboxylic acid, carbamide. We could also have carbaldehyde, right? So you could put so the carbo is giving us that 1 extra carbon in the parent name. Okay. So if we look at the reactivity, so let's go ahead and get started. I think we have enough time to get started on this. So if we look at what's going to happen with most of our carboxylic acid derivatives, right? And I'm going to put a Y here so it doesn't infer. You're going to get a nucleophile attacking your carbonyl, right? So this nucleophile is going to attack that carbonyl, pi bond's going to go up. And then at this point, right, the electrons could come back down and kick the nitrogen back off. So we could think about this coming down here, kicking the nucleophile off, to go backwards, right? Or the electrons could come down and kick the Y group off. So for the reactivity of carboxylic acids, we're not going to have nucleophilic addition reactions. We're going to have nucleophilic substitution reactions. And the big part of this is that the Y is the leaving group. And so that Y being the leaving group, that's going to be the thing that determines how well that leaving group is. Right? Is going to determine the reactivity of our carboxylic acid derivatives. So if we look at these, right, we got the carboxylic acid, acid chloride. If this reacts with the generic nucleophile, what's lost, right, is the chloride. We take the anhydride, right, react it with the generic nucleophile. What's left is, what leaves is the carboxylate, right? We take an ester, we end up with the methoxide. We have an amide. We have the amide. So consider these leaving groups. Is the chloride a good leaving group? Yes. Is the acetate a good leaving group? Yeah. How about the methoxide? Well, is it really basic? Does the oxygen negative happy being the oxygen negative? Can I use this as a good nucleophile? Yes, right? So we're getting to the point where it's like, maybe. What about the amide, the NH2 minus? Is this a strong base? Oh yeah, it's a strong base, right? I can use it to deprotonate a proton on an acetylide, right? To make an acetylide. So, that's not a good leaving group. So when we look at this and we look at the reactivities, it all has to do with this leaving group. So that means the chloride is going to be a better, more reactive than the anhydride, than the ester, right, than the amide. And to the point, right, that if we look at the reagents, we can think about mild, right, probably mild, medium, right, strong, right? Because if we think about what's leaving, are we going to get an NH2 minus to leave? No, it's not going to want to leave as an NH2 minus. We're going to have to do something to create it to want to leave. That might be using an acid, or that might be using a whole lot of heat, right? So as we look at these reactivities, what we need to think about is the number one reaction for carboxylic acid derivatives is nucleophilic substitution, and that's driven by the leaving group. So acid chlorides are going to be your most reactive, right? Then your anhydrides, then your esters, and then your amides. And the reactions in these different groups as they react are going to be dependent upon that leaving group. So